In this video, we are going to study definition of Laplace transform. So, in previous unit, we have studied Fourier transform, where signals are being converted from time domain to frequency domain. So here, Laplace transform, we can assume it to be like it is an advanced version of the Fourier transform. So, the role of Laplace transform is to convert time domain signal into a frequency domain signal. Now, the question is arising like, if we have Fourier transform that converts time domain signal into frequency domain, then why there is need of Laplace transform? The answer to this question is a word called as non-absolutely integrable signals. Now remember here, the limitation of Fourier transform is that if signal is non-absolutely integrable, Fourier transform cannot convert this signal from time to frequency. Therefore, Laplace transform plays an important role in such cases. So if signal is non-absolutely integrable, means if we integrate, the meaning of this non-absolutely integrable signal means if I integrate a signal from minus infinity to plus infinity x of t dt, this value should be less than infinity. Then the signal is called as absolutely integrable. But if this value becomes equal to infinity, then signals are said to be non-absolutely integrable signals. So, in case of Fourier transform, all the signals of which we can find out Fourier satisfies this equation, that integration of x of t signal from minus infinity to plus infinity, it will result into certain finite value. It will not be equal to infinity. But there are certain signals like, let's say example of our ramp signal. If we try to integrate this ramp signal from minus infinity to plus infinity, ramp is simply t into u of t dt. If we integrate this signal, the answer becomes infinite. So, for a ramp signal, we cannot convert ramp signal from time to frequency using the Fourier transform. In such cases, we need to use Laplace transform. So, a simple definition of Laplace transform. Laplace transform is advanced version of Fourier transform used to convert non-periodic, which is applicable to Fourier also, non-periodic and non-absolutely integrable signals which we cannot convert from time to frequency using Fourier from time to frequency domain. So Laplace transform converts non-periodic, non-absolutely integrable signals from time to frequency domain. So it is simply a tool or a mathematical tool which converts time domain signal into frequency domain. We know why we need to convert time domain into frequency domain, because certain parameters of signals which are not visible in time domain, those parameters can be made visible in frequency domain. So we use the Laplace transform to convert time domain signals into periodic signals, time domain signals into frequency domain signals, but those signals are non-periodic and non-absolutely integrable signals. So now let us go with the equation of Laplace transform. So Laplace transform and its basis function, it is given as x of s. So here in case of frequency, we are representing the frequency domain using omega or f. Here in Laplace, we are going to represent frequency domain using small s. So as we have frequency domain, the representation letters are always capital. So x is capital is equal to integration from minus infinity to plus infinity x of t, this is the time domain signal, into e raised to minus st dt. Similarly, we have equation for inverse Laplace transform as x of t equal to integration from minus infinity to plus infinity x of s into e raised to plus st ds. So here in Laplace transform the basis function is with negative sign, and in inverse Laplace transform the basis function is with positive exponential term. So this is the equation for Laplace transform. So we are going to solve numericals based on these equations of Laplace transform.